Okay, so this is question 10. We have the voltage to current converter. Okay, and uh, basically we have three options here, and we have to evaluate if they suit for a voltage to current converter. So the objective here is that we should be able to find out an equation for each one of the circuits where the current IL, okay, it depends on a constant K, and the input voltage Vi. The first circuit that we have is a simple passive circuit based voltage to current converter, and this is just like a voltage divider, right? So we can calculate IL. So in this first circuit, we can calculate IL as Vi times RL divided by R plus RL. Now, the thing here is that this voltage to current converted, it should be, so as you see here, independent, so let me just draw here, independent of the load resistance, RL. Now, if we analyze this, so if we analyze this equation that we just got, the term K here, that it should be constant, right? It actually depends on RL. So this particular circuit, it wouldn't be like a very good voltage to current converter, regarding that its constant K depends on the load resistance, right? So this wouldn't be like a good voltage to current converter. Now this second option here, it's more interesting, although a little bit tricky, and I will basically show you my analysis and basically what's the drawback of this circuit from my perspective. Okay, so first, remember that if we consider the op-amp as an ideal operational amplifier, we know that, so let me use like a thinner here and thinner here. Okay, so if you remember, for an ideal op-amp, we know that V minus equals to V plus, right? And in this case here, we know that V minus is equals to Vi. Cool. So we have Vi up here, right? So if we have Vi over here and the ground here, and we are grounded also here, right? The current that we observe, it's kind of tricky, but the current that we observe that's flowing here should also be flowing here as IL, right? So in this particular case, we could say that IL is equals to the voltage here minus the voltage there. So it's Vi because it's V minus, right? Divided by R. And now if you look at this equation here, basically this one here, the constant term is just like 1 over R, right? So this would be like a good, it fits the condition that our current, load current, should basically depend on the input voltage, right? And times some constant, and this constant here is just R, okay? But the thing is that if we keep decreasing this voltage, so remember that here we have V plus, or Vi, sorry, right? So if we have Vi, we could say that this voltage here, this current, it's also like V naught minus Vi divided by RL, right? If we want to derive this equation here. So we could also say that IL here, it's equals to V out minus Vi, so it's just minus Vi divided by RL. So in this particular, from my understanding, in this particular case, if we keep decreasing or if we keep changing the value of RL, we are also changing the value of IL. And although we would have the same current flowing here, the rest of the current that should be flowing here, or like in the opposite direction, it should come from the inside of the operational amplifier. And eventually, for a very low value of RL, this current would be high enough to basically burn our operational amplifier. So that's from my understanding. So that's a kind of a drawback from this particular circuit here. Okay, so it's not the best option right now. Now for the third circuit, this one is more interesting and a little bit more complicated, but it's more interesting. So again, for this particular circuit, we know that for an ideal operational amplifier, V plus is equals to V minus. There is no current flowing inside the op amp, right? So the first step, we can define what's the value of V minus, okay? Because if we know the voltage here, we know the voltage there. And remember, that's no current in here, no current in there. So if we analyze, if we apply KCL at this node here at V minus, we get an equation that is V minus minus 0 divided by R plus V minus minus V out divided by R, and that should be equals to 0. So if we manipulate this equation, we get that V out, or like V minus, is equals to V out divided by 2. Okay, so this is the first equation that we get. And remember that V minus is equals to V plus. Okay, so if we know the voltage here, we know the voltage there. So we know the voltage here, and we also know the voltage that's applied through the RL here, which can give us IL. Okay. Okay, so if we analyze now the non-inverting input, we get first the current that, so let me put this one here to change. So we get that V plus minus VI divided by R, which is this current here, plus V plus minus V out divided by R, which is this current here, plus V plus minus 0 divided by RL should be 0, which is this last current here, IL. Okay, so we have this equation here, and since we know that V plus is equals to V naught over 2, we can substitute V naught over 2 here, and then we basically get that, so V naught over 2R plus V naught over 2R for this term here and this term here, plus V naught over 2 RL minus VI over R minus V naught over R, which is this term here, should be equals to 0. So this one here with this term here, they cancel out, because it's half V naught plus half V naught. It's just V naught over R minus V naught over R. This leads to V naught equals to VI over R times 2RL. So that's the equation for V out, okay, in respect to VI. And we know that the voltage, we know that the current IL here is just, so we know that IL, the load current, is equals to V plus divided by RL, right? So it's V plus here minus 0 here divided by RL. That's IL. This is the same as, because we know that V plus is equals to V minus is equals to V minus divided by RL. We know that V minus is equals to V naught over 2. So IL is equals to V naught over 2 RL. And we know that V out is equals to VI to RL divided by R. So this is equals to VI times 2 RL divided by R times 2 RL. So these terms here, they cancel out. And our final answer is just IL equals to VI times 1 over R. This is the final answer. Okay, and this is our K. So this answer here, it's the answer that we are looking for. IL equals to VI, so the voltage to current converter. So it depends on the input voltage and some constant. So if we want to change the current here, we just have to change VI, of course, but we also could change the K here just by changing R. And another thing is that if we use a load resistance, right, that is zero, like a short circuit, the voltage here at the output will be clipped by the voltage that we are basically feeding our op-amp. So the internal circuit of the op-amp, remember that we have some terminals here and terminals here that we use as plus VDD and minus VDD. So those are the maximum voltage that we can observe at the output of the operation amplifier. So we are basically limiting, basically if we use like a very high value of RL here, we limit our voltage to be something that it's clipped, right, by the maximum voltage that we are feeding. But the load resistance, the load current here won't be affected by that RL. And if it is a zero, like a short circuit, right, then we would have like a voltage here that's zero at the output. But even in that case, we would get something at the load resistance here that basically gives us this load current. So this is the best approach, and this is the equation that we get for this circuit.